Welcome to Most Relaxing Facts. Tonight, we're leaving Earth behind. We're drifting away from the noise and the light, moving beyond the atmosphere, past the moon, into the infinite quiet of deep space. Out here, among the stars and nebulae and distant worlds, there is a profound stillness, a peace that stretches across billions of miles. Over the next few hours, I'll guide you gently through the wonders of the cosmos. Each fact, a small light in the darkness. Each discovery, a reminder of how vast and beautiful the universe truly is. Let these cosmic truths carry you softly towards sleep, as weightless as an astronaut floating in the velvet black. If you find comfort in these journeys through the most fascinating corners of our universe, please take a moment to like this video and subscribe to Most Relaxing Facts. Your support helps us explore new worlds together. But for now, let's prepare for our voyage into the stars. Take a deep, slow breath in. Hold it for just a moment and release it gently, letting all the tension flow away. Feel yourself becoming lighter, quieter, ready to drift through the cosmic ocean where time moves differently and distance loses all meaning. Close your eyes if you wish, or keep them softly open, gazing into the darkness. Our journey into deep space begins now. Close your eyes and let me take you on a journey beyond our world. Tonight, here on Most Relaxing Facts, we're going to drift together through our cosmic neighborhood, not in a rushing spaceship with roaring engines, but floating peacefully, slowly, through the vast silence where no sound can travel. We'll visit the sun that lights our days and the silent giants that circle it, the worlds of ice and fire, of crushing storms and razor-thin rings, of mountains made of frozen water and winds faster than anything on Earth. Imagine yourself suspended in the perfect quiet of space, where silence is not the absence of noise, but something deeper, something absolute. Around you, the planets perform their ancient dance, spinning and orbiting in patterns that have continued for billions of years. The sun glows warm and constant, and you are weightless, peaceful, drifting through the solar backyard where our little Earth is just one small marble among giants. Tonight we'll explore this neighborhood of ours, discover why Venus burns hotter than an oven and why Saturn's magnificent rings are thinner than a building is tall. Learn about the storm on Jupiter that has raged for 3 centuries and the spacecraft that carries the sounds of Earth into the eternal darkness between stars. So settle in, get comfortable, and let your mind drift outward, past the atmosphere, past the moon, into the realm where physics becomes poetry and distance becomes so vast that light itself takes minutes to cross it. Let's begin our quiet journey through the solar system. Space is almost a perfect vacuum. Unlike Earth, where air carries sound waves from your voice to someone's ear, where wind rustles leaves and thunder rolls across the sky, space has almost nothing. No air molecules to vibrate, no medium for sound to travel through. In the deepest voids between planets, between stars, the silence is absolute. This silence is difficult for our minds to truly grasp. We've never experienced it. Even in the quietest room on Earth, there's still air, still the sound of your own breathing, your heartbeat, the blood moving through your ears. But in space, there is nothing. Complete, total, profound silence. This silence means that the universe's most dramatic events, stars exploding in supernovae, black holes consuming matter, cosmic collisions of unimaginable violence, all happen in perfect quiet. The explosion that would deafen you on Earth occurs soundlessly in space, their energy traveling as light and radiation, but never as sound, never as anything your ears could perceive. The sun sits at the center of everything in our solar system, and its dominance is almost total. This massive sphere of burning hydrogen accounts for 99.86% of all the mass in our entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust, makes up less than 1/7 of 1%. This proportion is staggering. Jupiter, our largest planet, seems massive to us. But compared to the Sun, Jupiter is a rounding error, a tiny fraction of the total mass. Earth is barely noticeable. We think of our world as substantial, as the ground beneath our feet, as something solid and significant. But in solar system terms, we're nearly nothing. A speck orbiting a furnace that contains almost everything. The sun's gravity shapes everything in our neighborhood. The planets orbit because they're caught in the sun's gravitational well, moving fast enough not to fall in, but not fast enough to escape. The sun's influence extends far beyond what we can see, far past the outermost planets, creating an invisible architecture that holds our solar system together. To understand the scale, imagine the sun is the size of a typical front door, about 7 feet tall. On this scale, Earth would be roughly the size of a nickel, a small coin you could hold between your fingers. This nickel Earth would be sitting about 25 feet away from the door sun, orbiting in a circle, tiny and distant. Jupiter, the largest planet, would be about the size of a basketball on this scale. Still significant, but dwarfed by the door-sized sun. And the distances become almost comical. Neptune, the outermost major planet, would be nearly 1/10 of a mile away. The solar system is mostly empty space, vast distances separating tiny objects, all held together by gravity's invisible threads. This scale helps explain why space travel is so difficult, why missions to other planets take years, why even communication with spacecraft near other planets involves delays as radio signals cross the enormous distances between worlds. When you look at the sun, and you shouldn't look directly, but when you see it in the sky, you're not seeing it as it is now. You're seeing it as it was 8 minutes and 20 seconds ago. This is how long light takes to travel from the sun's surface to your eyes, crossing the 93 million miles between star and planet at the speed of light, the fastest thing in the universe. This time delay is brief by cosmic standards, but it's still a form of time travel. The photons hitting your retina were created in the sun's core through nuclear fusion, worked their way to the surface over thousands of years, then shot across space for 8 minutes and 20 seconds before being absorbed by your eye and converted into the sensation of light. If the sun suddenly vanished, impossible, but imagine, we wouldn't know for 8 minutes and 20 seconds. For that brief time, Earth would continue orbiting a sun that was no longer there, illuminated by light that was already in transit, living in a past that had already ended. Then, after that delay, darkness would arrive with the gravity wave, and we'd know the sun was gone. Venus is Earth's near twin in size, similar in mass and composition, close to us in the solar system. But Venus is hell. Its atmosphere is so thick with carbon dioxide that the surface pressure is 90 times greater than Earth's, equivalent to being 3,000 feet underwater. and the temperature is 460 degrees Celsius, hot enough to melt lead in minutes. This heat is hotter than Mercury, even though Venus is farther from the Sun. The reason is Venus's atmosphere, a runaway greenhouse effect where carbon dioxide traps heat so efficiently that the planet can't cool down. The thick clouds that make Venus bright in our sky are made of sulfuric acid, and they create an oven that bakes the surface continuously. But Venus has another peculiarity. It rotates incredibly slowly. One rotation, one Venus day, takes 243 Earth days. But one orbit around the Sun, one Venus year, takes only 225 Earth days. This means a day on Venus is longer than a year on Venus. If you stood on the surface, which you couldn't survive, you'd watch the Sun rise in the west, slowly arc across the sky over many Earth months, and set in the east, all while Venus completed more than one orbit around the Sun. This slow rotation, combined with the retrograde direction, opposite to most planets, creates a strange rhythm where a solar day on Venus, sunrise to sunrise, actually lasts 117 Earth days. Time moves differently there, stretched and distorted by rotation and orbit, combining in unusual ways. Mercury, the closest planet to the Sun, experiences temperature extremes that seem impossible. During its long day, which lasts 176 Earth days, the side facing the Sun heats to around 430 degrees Celsius. But during its long night, without any significant atmosphere to trap and distribute heat, the temperature plummets to negative 180 degrees Celsius. This is a swing of over 600 degrees Celsius between day and night, the most extreme temperature variation in the solar system. The surface of Mercury is a place of incredible hostility, alternately baked and frozen, with no comfortable middle ground, no moderate zone where water could exist as liquid, where life as we know it could possibly survive. Mercury's lack of atmosphere also means its surface is heavily cratered, directly exposed to the impacts of asteroids and comets, with no air to burn up smaller objects before they strike. The planet is a record of bombardment, its face scarred by billions of years of cosmic collisions, each crater preserved because there's no erosion to wear them away. Our moon, Earth's constant companion, is slowly leaving us. Each year, the moon drifts about 3.8 centimeters farther from Earth, roughly the same speed that your fingernails grow. This movement is caused by tidal forces, the same forces that create ocean tides on Earth. The Earth's rotation is gradually slowing down, and the energy from this slowing is transferred to the moon's orbit, causing it to spiral very slowly outward. This process has been happening for billions of years. Early in Earth's history, the moon was much closer, appearing larger in the sky, creating more extreme tides, orbiting faster. Eventually, billions of years from now, the moon will have drifted so far away that it will appear much smaller in our sky, creating less dramatic tides, taking longer to orbit. The process will eventually reach equilibrium, but not for a very, very long time. For now, the moon continues its slow departure, a centimeter here, a centimeter there, gradually increasing the distance between Earth and its only natural satellite. This drift also means that total solar eclipses, where the moon perfectly covers the sun, will eventually become impossible. The moon will be too far away, too small in the sky, to completely block the sun's disk. We live in a special time when the moon is at just the right distance to create these perfect alignments, these moments when day turns briefly to night, and can see, the Sun's corona. Mars, the red planet, is home to Olympus Mons, the largest volcano in the solar system. This shield volcano, a type that forms from fluid lava flows rather than explosive eruptions, is 3 times taller than Mount Everest, rising about 21 kilometers above the Martian surface. Its base is roughly the size of the state of Arizona, covering an area of about 300,000 square kilometers. Olympus Mons is so large that if you stood on its summit, you wouldn't be able to see the base. The horizon would curve away before you could see the bottom. And if you stood at the base looking up, you wouldn't be able to see the summit. The volcano is so vast that its slopes disappear into the distance, creating a landscape that rises imperceptibly toward the sky. The volcano is likely extinct now, or at least dormant, having not erupted for millions of years. But its size testifies to Mars's different geology compared to Earth. On Earth, tectonic plates move, carrying volcanoes away from their magma sources, creating chains of volcanoes like Hawaii. But Mars has no plate tectonics, so volcanic hotspots can build in one place for millions of years, creating these enormous structures. The dust on Mars is incredibly fine as talcum powder, and it has a property that makes it particularly troublesome for missions to the surface. It's highly electrostatic. The dust particles develop static charges from rubbing against each other in the wind, and these charges make the dust cling to everything it touches. This sticky dust has been a problem for every Mars rover. It coats solar panels, reducing their efficiency. It works its way into mechanical joints. It obscures cameras. The rovers have various methods for dealing with the dust: brushes, air jets, even taking advantage of wind to blow dust away. But it remains a constant challenge, a reminder that Martian conditions are hostile in ways beyond just the thin atmosphere and cold temperatures. The dust also creates Mars's famous planet-wide dust storms, which can last for months and cover the entire globe, turning day into twilight, making it impossible for solar-powered spacecraft to function. These storms are driven by temperature differences and Mars's thin atmosphere, which allows dust to be lifted high into the air and carried around the planet by high-altitude winds. Jupiter is a gas giant, meaning it has no solid surface at all. The planet is made mostly of hydrogen and helium, the same elements that make up the Sun, compressed by gravity into layers of increasing density. If you tried to stand on Jupiter, there would be nothing to stand on. You would simply sink deeper and deeper into the atmosphere until the pressure and temperature became so great that the distinction between atmosphere and interior became meaningless. As you descended, the atmosphere would grow thicker and hotter. Eventually, at depths where the pressure is millions of times greater than Earth's atmosphere, hydrogen is compressed so tightly that it becomes metallic, a strange form of matter that conducts electricity like metal but is still fundamentally hydrogen. Jupiter's magnetic field, which is the strongest of any planet in the solar system, is generated in this layer of metallic hydrogen. At Jupiter's very core, there may be a small rocky core, a seed around which the gas giant formed. But even this is uncertain. We can't see into Jupiter's depths, can only infer what exists there from gravity measurements and theoretical models. Jupiter remains mysterious, despite being so large, its interior hidden beneath clouds and crushing pressure. The Great Red Spot is Jupiter's most famous feature, a massive storm in the planet's southern hemisphere that has been continuously observed for at least 300 years and probably has existed much longer. This storm is so large that it could swallow 2 Earths. It rotates counterclockwise, completing one rotation every 6 days, driven by winds reaching 400 miles per hour at its edges. The storm's red color comes from complex organic molecules created by sunlight interacting with the chemicals in Jupiter's atmosphere, though the exact chemistry is still debated. The color intensity varies over time. Sometimes the spot is brick red, sometimes it fades to a pale pink, and the reasons for these changes aren't fully understood. The Great Red Spot has been shrinking. Historical observations show it was much larger in the past, and recent measurements show it continues to get smaller. Eventually, it may dissipate entirely, this centuries-old storm finally running out of energy. But for now, it persists, a monument to Jupiter's dynamic atmosphere, a storm that has raged longer than any nation on Earth has existed. Saturn's rings are one of the solar system's most beautiful features, delicate bands of light encircling the planet, visible even through a small telescope, creating an image that seems almost too perfect to be real. But these rings are not solid structures. They're made of billions of individual particles, each one orbiting Saturn independently, ranging in size from grains of sand to pieces as large as houses. The particles are mostly water ice, though they also contain rock and dust. They're thought to be either remnants of a moon that broke apart or material that never coalesced into a moon in the first place. Each particle is essentially a tiny moon, following its own orbit, colliding occasionally with neighboring particles, creating a dynamic system that's constantly reorganizing itself. The rings are incredibly thin relative to their width. While they extend 175,000 miles from Saturn's center, they're only about 30 feet thick in most places, thinner proportionally than a sheet of paper. If you could somehow stand at the edge of the rings and look along them, they would appear as an impossibly thin line, a mathematical plane rather than a physical structure. This thinness makes the rings fragile in cosmic terms. Collisions and gravitational perturbations constantly erode them, and scientists believe the rings may be relatively young by solar system standards, perhaps only a few 100 million years old. They may disappear in another 100 million years or so, eroded away by various forces, meaning we're seeing Saturn's rings during a brief window of cosmic time when they happen to exist. Uranus is strange among the planets. It rotates on its side, its axis tilted 98 degrees from perpendicular to its orbital plane. This means Uranus essentially rolls around the Sun like a ball, with each pole spending decades in constant sunlight, followed by decades in constant darkness. This extreme tilt is thought to be the result of a massive collision early in the solar system's history, when a large object struck Uranus with enough force to knock it onto its side. The planet has maintained this orientation for billions of years, creating bizarre seasonal patterns where the poles are sometimes warmer than the equator, where the pattern of sunlight is unlike anything experienced on Earth. Uranus is also notable for being relatively featureless when viewed through telescopes, a pale blue-green ball without the dramatic clouds of Jupiter or the rings of Saturn. This calmness is deceptive. Uranus does have weather and clouds, but they're subtle, visible only in enhanced images. The planet is quieter than the other gas giants, colder, more distant, less understood. Neptune, the most distant of the major planets, experiences the fastest winds in the solar system. Winds at Neptune's equator can reach 200 miles per hour, faster than the speed of sound on Earth, faster than any terrestrial tornado or hurricane, driven by internal heat and the planet's rapid rotation, despite being so far from the sun that solar heating is minimal. These winds create storms and features in Neptune's atmosphere. The Great Dark Spot, similar to Jupiter's Great Red Spot, but smaller and less permanent, was observed by Voyager 2 in 1989, but had disappeared by the time the Hubble Space Telescope looked for it a few years later. Neptune's weather is dynamic, changing on timescales of years, driven by forces we don't fully understand. Neptune is so distant that it receives 900 times less sunlight than Earth. At that distance, the Sun appears as just a very bright star, no longer a disk, but a point of light. Yet Neptune radiates more heat than it receives from the Sun, suggesting that the planet has significant internal heat sources, energy left over from its formation billions of years ago, still slowly dissipating into space. The asteroid belt lies between Mars and Jupiter, a region of space containing millions of rocky objects that never coalesced into a planet. Popular culture often depicts this belt as a crowded, dangerous field that spacecraft must carefully navigate, but the reality is very different. The asteroid belt is mostly empty space. If you were in the belt, you probably wouldn't see another asteroid with the naked eye. They're separated by hundreds of thousands of miles on average. The total mass of all asteroids combined is less than our Moon's mass. This is a sparse, quiet region, not the chaotic obstacle course of science fiction. The asteroids themselves are ancient, remnants from the solar system's formation, preserved in deep freeze for 4.6 billion years. Studying them gives us insights into what the early solar system was like, into the material that formed the planets, into the conditions that existed when Earth was being born. Pluto, demoted from planet status in 2006 but still beloved, has mountains made of solid water ice. These mountains, some reaching heights of 11,000 feet, are frozen so hard that they behave like rock, maintaining steep slopes and sharp peaks despite being made of H2O. The mountains are young by solar system standards, probably less than 100 million years old, suggesting that Pluto is geologically active despite being so cold and distant. The processes shaping Pluto's surface are still being discovered and debated, but it's clear that this small world is more dynamic than anyone expected. Pluto orbits in the Kuiper Belt, a region of space beyond Neptune filled with icy bodies, frozen remnants from the early solar system. These objects haven't changed significantly since the solar system formed. They're too cold, too distant, too far from the sun's heat to have experienced the geological activity that transformed the inner planets. They're time capsules, preserving information about the solar system's birth. Even farther out lies the Oort cloud, a vast spherical shell surrounding the entire solar system, extending perhaps halfway to the nearest star. This cloud may contain trillions of icy objects, comets waiting in frozen sleep, so distant that they're barely bound to the sun's gravity, so cold that they're at nearly the temperature of interstellar space. The Oort cloud has never been observed directly. The objects are too small and too far away for our telescopes to detect. We know it exists because comets come from there, occasionally knocked into the inner solar system by gravitational perturbations, falling toward the Sun and creating the spectacular displays we see from Earth. But the Oort cloud itself remains theoretical, invisible, a dark frontier we can only study indirectly. Voyager 1, launched in 1977, is now the farthest human-made object from Earth. It's traveling through interstellar space at about 38,000 miles per hour, having passed beyond the influence of the Sun's solar wind, beyond the heliopause, beyond the boundary of our solar system, into the space between stars. Voyager 1 carries the golden record, a phonograph record containing sounds and images from Earth, thunder and rain, bird songs and whale calls, greetings in 55 languages, music from different cultures and eras. The record is encased in a protective aluminum cover with instructions for how to play it, etched in symbols we hope would be comprehensible to any intelligence that finds it. The record is a message in a bottle thrown into the cosmic ocean. The chances of it being found are infinitesimally small. Space is vast, and Voyager is tiny. But it represents hope and optimism, the idea that we might make contact, that we're not alone, that our sounds and images might someday reach ears and eyes we can't imagine. In space, if two pieces of the same type of metal touch in vacuum, they will permanently bond together through a process called cold welding. On Earth, metal surfaces are covered with oxide layers and contaminants that prevent bonding. But in the vacuum of space, without these barriers, the metal atoms don't know which piece they belong to. They bond together as if they were always one piece. This phenomenon has caused problems for spacecraft, where metal parts that weren't supposed to stick together ended up bonded. It's one of the many ways that the space environment is hostile and strange, where the normal rules of Earth don't apply, where engineers must account for effects that never occur in terrestrial conditions. The Moon has no atmosphere, no wind, no water. The footprints left by Apollo astronauts in the lunar dust will remain there for millions of years, unchanged, preserved in the airless environment. Every boot print, every rover track, every disturbed patch of dust, all of it stays exactly as it was left, a permanent record of human presence. These footprints are museums of themselves, monuments to the brief time when humans walked on another world. Unless they're hit by meteorites or disturbed by future missions, they'll remain, outlasting nations and civilizations, outlasting perhaps the species that made them, a testament frozen in time on a dead world. At the very edge of our solar system, about 11 billion miles from the Sun, lies the heliopause, the boundary where the solar wind, the stream of charged particles flowing out from the Sun, meets the interstellar medium, the thin gas between stars. This is where the Sun's influence fades, where our local bubble gives way to the larger galaxy. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. The transition was subtle. There was no wall, no dramatic change, just a gradual shift in the types of particles detected, a realization that the spacecraft was now immersed in the cold breath of the galaxy rather than the warm breath of the Sun. This boundary is where our solar backyard ends and the true cosmic wilderness begins. Beyond the heliopause, we're in the realm between stars, in the vast dark spaces that separate the pinpoints of light, in the territory that takes thousands of years to cross even at Voyager's speed. Let these facts settle gently into your mind. The absolute silence of space where no sound can travel. The sun containing 99.86% of everything. Earth as a nickel compared to the sun's front door. Light taking 8 minutes and 20 seconds to reach us. Venus, where a day is longer than a year. Mercury's 600-degree temperature swings. The moon drifting away at fingernail-growing speed. Olympus Mons 3 times taller than Everest. Jupiter's great red spot raging for 300 years. Saturn's rings thinner than a sheet of paper, but 175,000 miles wide. Uranus rolling on its side. Neptune's 1,200-mile-per-hour winds. The mostly empty asteroid belt. Pluto's ice mountains 11,000 feet high. The Kuiper Belt's frozen time capsules. The Oort cloud's trillions of invisible objects. Voyager 1 carrying Earth's sounds into the darkness. Cold welding in the vacuum. Footprints on the moon lasting millions of years. And the heliopause where the sun's influence fades into galactic cold. This is our solar backyard, our local neighborhood in the cosmos. These are the worlds that share our star, that orbit with us through the galaxy, that have remained largely unchanged for billions of years. Rest here in the peaceful quiet of space, where planets spin in silence, where storms rage without sound, where time moves differently and distances are measured in light and years. And when you're ready, we'll venture farther, beyond our sun's family, into the realm of stars and galaxies, into the deeper cosmos where even more wonders await. We venture now beyond our solar backyard, beyond the familiar planets and their moons, into the realm where stars are born and die, where nebulas bloom like cosmic flowers and black holes bend the very fabric of space and time. This is the Stellar Cradle, the deep void where creation and destruction dance together in slow motion, measured in millions of years, where matter collapses and explodes and transforms, where the atoms in your body were forged in the hearts of dying suns. Let us drift together through these cosmic nurseries and graveyards, through clouds of gas larger than you can imagine, and objects smaller than Earth but heavier than our sun. Let us discover why stars come in different colors, why some spin hundreds of times per second, why time itself slows near the most massive objects. Let us learn that we are made of stardust, that the iron in our blood was created in stellar furnaces, that every atom in our bodies has existed since nearly the beginning of time, recycled through stars and planets, and now briefly arranged into the pattern that is you. Stars are born inside massive clouds of dust and gas called nebulas, often referred to as stellar nurseries. These clouds are the raw material of creation, the primordial substance from which suns and planets form. A nebula might be dozens or hundreds of light years across, containing enough material to create thousands of stars, floating in the darkness, waiting for some trigger. A nearby supernova's shockwave, a collision with another cloud, to begin the collapse. When regions within a nebula become dense enough, gravity takes over. The gas and dust begin to fall inward, contracting, heating up from the compression. As the center gets denser and hotter, the temperature eventually reaches millions of degrees, hot enough for nuclear fusion to begin. Hydrogen atoms fusing into helium, releasing enormous amounts of energy. A star is born, a new light appearing in the cosmos, pushing back against gravity with the pressure of its own nuclear fire. The pillars of creation in the Eagle Nebula are perhaps the most iconic stellar nursery, made famous by the Hubble Space Telescope's stunning image. These pillars are giant plumes of cosmic gas, each one over 4 light-years tall, so large that if you placed our entire solar system at their base, the orbit of Neptune would barely reach a fraction of the way up. These pillars are being both created and destroyed. New stars are forming inside them, hidden within the dense gas and dust, but the intense radiation from nearby young stars is also eroding the pillars, evaporating them slowly, sculpting them into these dramatic shapes. The pillars we see now may already be gone. Remember, the light takes time to reach us, and we're seeing these structures as they were thousands of years ago. They may have been completely evaporated by now, but their light, showing their destruction, hasn't reached us yet. A light year is the distance. Light travels in 1 year, about 6 trillion miles, or 9.46 trillion kilometers. This is the unit we use to measure cosmic distances because miles and kilometers become unwieldy. Even within our galaxy, distances are so vast that light years are the convenient measure, the way we express the space between stars. Light is fast, the fastest thing in the universe, traveling at 186,000 miles per second. At this speed, light can circle the Earth's equator 7.5 times in a single second. And yet, cosmic distances are so enormous that even light takes years to cross them. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. That means the light we see from Proxima Centauri left that star 4.2 years ago. We're seeing the past, looking at a star not as it is now, but as it was when that light began its journey. If we wanted to travel to Proxima Centauri using our fastest current spacecraft, it would take about 70,000 years. This puts interstellar travel in perspective. The nearest star, our closest stellar neighbor, is so far away that with our current technology, the journey would take longer than recorded human history. The cosmos is vast beyond human intuition, and the spaces between stars are almost incomprehensible gulfs of distance. Stars come in different colors based on their surface temperature. This seems counterintuitive at first. We think of red as hot and blue as cold, but in stellar terms, the opposite is true. Blue stars are the hottest, with surface temperatures of 25,000 degrees Celsius or more. White stars are somewhat cooler, around 10,000 degrees. Yellow stars like our Sun are about 5,500 degrees, and red stars are the coolest, around 3,000 degrees, though cool is relative when we're talking about temperatures that would instantly vaporize any known material. This color-temperature relationship is fundamental physics. As objects heat up, they emit light at different wavelengths. Cooler objects glow red. They get hotter. They shift to orange, then yellow, then white, then blue. Stars follow this same pattern, their colors revealing their temperatures, allowing astronomers to understand their properties just by looking at the spectrum of light they emit. The largest known star, UY Scuti, is almost incomprehensibly massive. If you replaced our Sun with UY Scuti, its surface would extend past the orbit of Jupiter. Earth, Mars, the asteroid belt, all would be inside the star, consumed, orbiting within the stellar material itself. The star is so large that if you were traveling at the speed of light, it would take about 7 hours to travel around its circumference. Stars like UY Scuti are rare, representing the extreme upper limit of stellar mass. They're unstable, constantly losing mass through stellar winds, their outer layers blown off by the intense radiation pressure from their cores. They can't last long by stellar standards. They burn their fuel so quickly that their lifetimes are measured in mere millions of years rather than the billions of years that smaller, more stable stars can survive. When massive stars die, their cores collapse under their own gravity, compressing matter to densities that seem impossible. What remains is a neutron star, an object about 20 kilometers across, containing more mass than our Sun, compressed so tightly that the atoms themselves have collapsed, their electrons forced into the nuclei, converting protons into neutrons. The density is staggering. A single teaspoon of neutron star material would weigh 1 billion tons, more than all the cars on Earth combined. This matter is compressed beyond anything we can recreate in laboratories, existing in a state where normal atomic structure doesn't apply, where matter becomes something fundamentally different from anything in our everyday experience. Some neutron stars spin incredibly fast, completing hundreds of rotations per second. These are pulsars, neutron stars with strong magnetic fields that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like lighthouse beams, and if Earth happens to be in the path of the beam, we detect regular pulses of radiation, hence the name pulsar. The fastest known pulsar rotates 716 times per second. Imagine an object more massive than the Sun, compressed to the size of a small city, spinning so fast that its equator is moving at a significant fraction of the speed of light. The physics of these objects challenges our understanding, operating at extremes of density, magnetic field strength, and rotation that we can barely model mathematically. The twinkling of stars, technically called scintillation, is caused by Earth's atmosphere. As starlight passes through the atmosphere, it encounters pockets of air with different temperatures and densities. These pockets act like lenses, bending the light slightly, causing the star's apparent position and brightness to shift rapidly. This creates the twinkling effect we see from the ground. In space, above the atmosphere, stars don't twinkle. They shine with steady, unblinking light, constant and unwavering. This is why space-based telescopes like Hubble can capture such clear images. They're not looking through the atmospheric turbulence that distorts the light, that limits what ground-based telescopes can resolve. Our Milky Way galaxy is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms extending from the ends of the bar. The galaxy contains an estimated 100 to 400 billion stars. The uncertainty in this number reveals how difficult it is to count stars in our own galaxy, much of which is obscured from our view by dust and distance. The Milky Way is about 100,000 light-years in diameter, and we're located about 26,000 light-years from the center in one of the spiral arms. From our position, we see the galaxy as a band of light stretching across the night. Sicker sky, the combined glow of billions of stars too distant to resolve individually, creating a river of light that has inspired myths and stories in every human culture. At the very center of our galaxy, hidden behind clouds of dust that block visible light but detectable through radio and X-ray observations, lies Sagittarius A, a supermassive black hole with about 4 million times the mass of our Sun. This black hole is dormant by cosmic standards, not actively consuming much material, but its gravity dominates the galactic center, with stars orbiting it at tremendous speeds. We've actually observed individual stars orbiting Sagittarius 8, tracking their movements over years and decades, using their orbits to calculate the black hole's mass. One star, designated S2, completes an orbit in just 16 years, reaching speeds of up to 3% of the speed of light at its closest approach to the black hole. These observations provide the strongest evidence that supermassive black holes exist at the hearts of galaxies. Black holes aren't actually holes, despite their name. They're regions where matter has been compressed so tightly that the resulting gravity is strong enough to prevent even light from escaping. A black hole is a point, or more accurately, a singularity, surrounded by an event horizon, a boundary beyond which escape becomes impossible. The event horizon isn't a physical surface, but a point of no return, defined by the escape velocity reaching the speed of light. Outside the event horizon, escape is still theoretically possible, though difficult. Inside the event horizon, all paths lead inward, toward the singularity. Not even light can escape because nothing can travel faster than light, and inside the event horizon, even traveling at light speed wouldn't be fast enough to overcome the gravity. If you fell toward a black hole, you would experience something called spaghettification, a delightful term for a terrifying phenomenon. The gravity of a black hole gets stronger very rapidly as you approach. If you were falling feet first, your feet would experience much stronger gravity than your head. This difference, this gradient in gravitational force, would stretch you, pulling your feet away from your head, elongating your body like taffy being stretched. For a stellar mass black hole, spaghettification would kill you long before you reached the event horizon, tearing your body apart at the molecular level. For a supermassive black hole like Sagittarius AE, the gradient is gentler, and you might actually survive crossing the event horizon intact, though you'd still be doomed, headed inevitably toward the singularity. Time behaves strangely near massive objects, an effect predicted by Einstein's general relativity and confirmed by countless experiments. Near a black hole, time slows down relative to an outside observer. If you could hover just outside a black hole's event horizon, which would require enormous energy to resist the gravity, and someone far away was watching you, they would see you moving in slow motion, your actions taking longer and longer as you got closer to the horizon. From your perspective, time would seem normal. You wouldn't feel any slowdown. But you'd notice that the rest of the universe seemed to be speeding up, time passing faster outside the black hole's influence. This time, dilation is real, measurable, and one of the most mind-bending consequences of relativity. The Orion Nebula is visible to the naked eye from Earth as a faint smudge in Orion's sword, hanging below the 3 stars of Orion's belt. This smudge is actually a massive stellar nursery, about 1,350 light-years away, where thousands of new stars are being born. Through a telescope, the nebula resolves into a complex cloud of glowing gas, illuminated by the young, hot stars forming within it. The Orion Nebula is relatively close by cosmic standards, making it an excellent laboratory for studying star formation. Astronomers have observed protostars within the nebula, young stars still gathering mass, still contracting toward their eventual stable state. The nebula is a chaotic, turbulent place with stellar winds and radiation from young stars blowing bubbles in the gas, sculpting the nebula's structure, creating the beautiful complexity we see. When a massive star, at least 8 times more massive than our Sun, runs out of fuel, it dies in one of the universe's most dramatic events, a supernova explosion. The star's core collapses in less than a second, rebounding with such violence that it blows the star's outer layers into space at speeds of up to 10% of the speed of light. A supernova can briefly outshine an entire galaxy, releasing in a few weeks as much energy as the Sun will produce over its entire 10 billion year lifetime. The explosion is so bright that historical supernovas have been visible during the day, appearing as new stars that gradually faded over weeks or months. Supernovas are more than just spectacular explosions. They're essential to cosmic chemistry. Most elements heavier than iron are created only in supernova explosions, forged in the extreme conditions of the collapse and explosion. The iron in your blood, the calcium in your bones, the gold in jewelry. All of these elements were created in supernovas, scattered into space, eventually incorporated into new planets and eventually into you. You are literally made of stardust. The atoms in your body are ancient, forged in stellar furnaces billions of years ago, scattered by supernovas, gathered into clouds that formed new stars and planets, eventually finding their way into the molecules that make up your cells. Every atom has a history stretching back to the earliest generations of stars, and every atom will continue existing long after you're gone, recycled into new forms, new planets, perhaps new life. You're a temporary arrangement of cosmic material, stardust, briefly organized into a pattern that thinks and feels and wonders about its own origins. Brown dwarfs occupy a middle ground between planets and stars. They're too massive to be planets, more massive than Jupiter, sometimes dozens of times Jupiter's mass, but not quite massive enough to trigger the hydrogen fusion that makes a star shine. They're often called failed stars, objects that almost became stars but didn't quite make it. Brown dwarfs do fuse deuterium, heavy hydrogen, for a time, and the most massive ones can fuse lithium, but they can't sustain the hydrogen fusion that powers true stars. They glow from the heat of their formation and from the limited fusion they can achieve, gradually cooling and fading over billions of years. They're difficult to detect, too cool to shine brightly, too small to be easily spotted, lurking in the darkness between stars. About half of all stars in our galaxy are part of binary systems, 2 stars orbiting their common center of mass. Some systems have 3 or more stars, creating complex orbital dynamics. Our Sun is unusual in being solitary, lacking a stellar companion. Binary systems can be close pairs, with the stars orbiting each other in hours or days, sometimes so close that they actually share material, with gas streaming from one star to the other. Or they can be wide pairs, with the stars separated by hundreds or thousands of astronomical units, taking centuries to complete an orbit. The variety of binary systems reveals the many possible outcomes of star formation, the different ways that stellar nurseries can produce multiple stars instead of single ones. When a star like our Sun exhausts its hydrogen fuel, it swells into a red giant, then eventually sheds its outer layers, leaving behind a white dwarf, the hot, dense core of the original star. A white dwarf is roughly Earth-sized, but contains about as much mass as the Sun, making it incredibly dense. though not as extreme as a neutron star. White dwarfs don't produce energy through fusion. They're done burning. They simply cool gradually, radiating away their stored heat over billions of years, fading from white to yellow to red, and eventually, given enough time, more time than the universe has existed so far, to black dwarfs, cold, dark, stellar corpses. White dwarfs are supported against gravity by electron degeneracy pressure, a quantum mechanical effect where electrons can't be compressed beyond a certain point. This pressure can support white dwarfs up to about 1.4 solar masses, the Chandrasekhar limit. Above that mass, even electron degeneracy pressure isn't enough, and the star collapses further, becoming a neutron star or black hole. The Crab Nebula is the expanding remnant of a supernova that was observed from Earth in the year 1054. Chinese astronomers recorded a guest star that appeared in the sky, visible even during the day for several weeks before gradually fading. We now know this was a supernova, and the Crab Nebula is what remains, a cloud of gas and dust still expanding outward from the explosion, currently about 11 light-years across and still growing. At the center of the Crab Nebula is a pulsar, the collapsed core of the original star, spinning 30 times per second, pumping energy into the nebula, creating the complex structure and beautiful filaments we see. The nebula is still energetic, still glowing brightly, a relatively young supernova remnant that will continue expanding and fading for thousands of years. Space isn't completely empty. Between stars lies the interstellar medium, a very thin gas, mostly hydrogen and helium, averaging about 1 atom per cubic centimeter. This seems like a vacuum by Earth standards. For comparison, Earth's atmosphere at sea level contains about 10 moles 19 molecules per cubic centimeter, but it's enough to affect passing light, to provide raw material for new stars, to carry magnetic fields and cosmic rays. The interstellar medium's patchy, denser in some regions, forming molecular clouds where stars will eventually be born, thinner in others, creating bubbles and voids blown clear by stellar winds and supernova explosions. This medium is the connective tissue of the galaxy, the stuff between stars that makes the galaxy a connected system rather than just isolated points of light. Dark matter is one of astronomy's greatest mysteries. We know it exists because its gravity affects the motion of stars in galaxies and the motion of galaxies in clusters. Galaxies rotate in ways that only make sense if they contain much more mass than we can see in stars and gas. Galaxy clusters hold together with gravity that requires much more mass than the visible matter provides. Dark matter makes up about 85% of the matter in the universe, yet we can't see it. It doesn't emit, absorb, or reflect light. We don't know what it's made of. Leading candidates include exotic particles that interact only through gravity and possibly the weak nuclear force. But despite decades of experiments, we haven't directly detected dark matter particles. Dark matter is invisible, intangible, detectable only through its gravitational effects. It's there, surrounding galaxies in vast halos, providing the gravity that holds galaxies together, shaping the large-scale structure of the universe. But what it actually is remains one of physics' deepest unsolved mysteries. When you look at stars at night, you're seeing ancient light. The light from stars has traveled for years, decades, centuries, or even millennia to reach your eyes. You're not seeing the stars as they are now, but as they were when that light left them. traveling across the vast darkness to finally end its journey in your eye. The star Betelgeuse in Orion is about 650 light-years away, so the light you see left that star around 1370 AD. If Betelgeuse exploded tomorrow, we wouldn't know for another 650 years. We're always seeing the past when we look at the sky, looking at a universe that no longer exists in the form we're seeing, experiencing the cosmos with a time delay built into the very nature of light and distance. Let these stellar facts rest gently in your thoughts. Stars born in nebulas called stellar nurseries, the pillars of creation, 4 light-years tall, light-years measuring 6 trillion miles. Proxima Centauri, our nearest star, 70,000 years away at current speeds. Blue star's hottest, red star's coolest. UY Scuti, extending past Jupiter's orbit. Neutron stars with 1 billion tons per teaspoon. Pulsars spinning hundreds of times per second. Stars twinkling from our atmosphere. The Milky Way's 100 to 400 billion stars. Sagittarius A, 4 million solar masses at our galaxy's heart. Black holes bending space and time. Spaghettification stretching you into a strand. Time dilation slowing clocks near black holes. The Orion Nebula creating thousands of new stars. Supernovas briefly outshining galaxies. You made of stardust. Atoms, forged in dying stars. Brown dwarfs, failed stars between planets and suns. Binary systems, half of all stars having companions. White dwarfs, Earth-sized with sun's mass. The Crab Nebula, supernova remnant from 1054. Interstellar medium, thin gas between stars. Dark matter, 85% of matter, invisible but present. And the old light of stars, showing us the past, never the present. This is the stellar realm, where stars are born and die, where the elements are forged and scattered, where gravity shapes time and space, where matter exists in forms impossible on Earth. Rest here in the cosmic nursery, among the dying giants and spinning pulsars, surrounded by nebulas blooming like flowers in the darkness. And when you're ready, we'll venture even farther, beyond our galaxy, into the realm of billions of galaxies, into the deepest structures of the universe, into the cosmic web, where everything connects. We drift now beyond our Milky Way, beyond the familiar spirals of our home galaxy, into the vast cosmic ocean where billions of galaxies float like islands in the darkness. Here, we discover worlds without suns, planets where glass rains sideways and diamonds form deep underground, galaxies colliding in slow motion across billions of years, and voids so empty that finding them challenged our understanding of the universe itself. Let us float together through this realm of alien horizons and rogue wanderers, through the space between galaxies where lonely planets drift in eternal night, through the strange physics of black holes so massive they outshine entire galaxies, through the mysterious forces that push the universe to expand faster and faster. Let us discover that our galaxy will one day merge with our neighbor, that space itself can ripple like water, that the universe still whispers its birth cry in every direction we look. Imagine a planet without a sun. No sunrise, or sunset. No seasons marked by changing light. Just eternal darkness, broken only by the faint glow of distant stars. These are rogue planets, worlds that wander through the void between stars, belonging to no solar system, orbiting no sun, adrift in the cosmic night. These lonely worlds weren't born in isolation. They formed around stars like other planets. But something went wrong. gravitational interactions with other planets, often with massive gas giants like Jupiter, kicked them out of their home systems. They were pulled and tugged by competing gravitational forces until finally they were flung out entirely, achieving escape velocity, leaving their sun behind forever. Now they travel through interstellar space, cold and dark, their surfaces frozen to temperatures barely above absolute zero. If they had atmospheres, those atmospheres might have frozen and fallen as snow, coating the surface in layers of frozen nitrogen or methane or whatever gases they once held. If they had oceans, those oceans are now solid ice, miles thick, covering whatever lies beneath. Astronomers estimate there may be billions of rogue planets in our galaxy alone, possibly outnumbering the stars themselves. This is astonishing. We think of planets as rare, as special objects orbiting stars. But the galaxy might be filled with these wanderers, these exiles, far more numerous than the stars they once orbited. Most of them are undetectable with current technology. Too cold, too dark, emitting almost no light or heat. But occasionally we spot one when it passes in front of a more distant star or through subtle gravitational effects. Some scientists speculate that rogue planets might not be entirely dead. A large planet with a thick atmosphere and internal heat from radioactive decay might maintain subsurface oceans, heated from below, isolated from the frozen surface by miles of ice. In these hidden oceans, shielded from the harsh radiation of space, protected by ice and darkness, could life exist? Could something live in an ocean that will never see sunlight, on a world that will never know a sunrise? We don't know, but the possibility haunts the imagination. Exoplanet HD 189733b orbits a star about 63 light-years from Earth, and it's one of the most hostile worlds we've discovered. This planet is a deep blue color. From Earth, it would look almost like a twin of our own blue marble. But the similarity is superficial and deceptive. The blue color doesn't come from water or from atmospheric oxygen. It comes from the atmosphere's composition, likely containing silicate particles that scatter blue light, similar to how our atmosphere scatters blue light, but for different chemical reasons. And this atmosphere is moving at incredible speeds. Winds on HD Y-Light-on-33b reach 4,500 miles per hour, faster than the speed of sound, creating supersonic jets that circle the planet. These winds likely carry clouds of silicate particles, essentially glass, and the theory is that on this world, it rains glass. Molten glass condenses in the atmosphere and falls as rain, except the rain doesn't fall straight down because the winds are so strong. The glass rain would move sideways, nearly horizontally, pelting anything in its path at incredible speeds. Standing on this world, if you could somehow survive, would mean being sandblasted by supersonic glass particles, a form of weather so hostile it seems almost malicious. The planet 55 Cancri E is even stranger. This super-Earth orbits very close to its star, completing an orbit in just 18 hours. The surface temperature is estimated at over 2,400 degrees Celsius, hot enough to melt rock. But what makes this planet particularly remarkable is its composition. Based on the planet's mass and density, researchers believe that at least 1/3 of the planet, and possibly much more, is made of carbon in the form of diamond. The immense pressure and temperature have compressed carbon into its crystalline form, creating a world that might have a diamond mantle beneath a thin coating of graphite and other materials. A diamond planet, an entire world made partly of gemstone, orbiting a distant star, forever out of reach but eternally glittering in ways we can only imagine. WASP-12b is a planet that absorbs 94% of the light that hits it, making it darker than coal, darker than asphalt, one of the blackest objects known in the universe. This hot Jupiter orbits extremely close to its star, tidally locked so that one side always faces the star, heated to extreme temperatures. The planet's atmosphere contains clouds of vaporized sodium and potassium, which absorb visible light, preventing it from reflecting back into space. The planet also appears to be losing mass, with material being pulled off its atmosphere by the star's gravity, creating a stream of gas flowing from planet to star. WASP-12b is slowly being consumed by its sun, gradually losing itself to the star it orbits, darkening as it dies, a charcoal planet being slowly devoured. J1407b is nicknamed Saturn on steroids because of its ring system, which is truly massive, far larger than Saturn's famous rings. The ring system extends out to about 90 million kilometers from the planet, with a diameter of about 180 million kilometers. That's roughly the distance from the Sun to Earth. If J1407b replaced Saturn in our solar system, its rings would be visible from Earth with the naked eye, appearing many times larger than the full moon, dominating the night sky, creating a spectacular sight that would have shaped all of human mythology and astronomy. The rings would be so large and bright that they would cast shadows on Earth, that they would be visible during the day, that they would define our view of the cosmos in ways we can barely imagine. The ring system shows gaps, suggesting that moons are forming within it, sweeping up material in their orbits, carving channels through the rings. We're seeing a planetary system in formation, watching the process of satellite creation in real time, or at least as real time as it gets, when the light has traveled for 434 years to reach us. Kepler 186f was a milestone in the search for Earth-like worlds. This planet is about 10% larger than Earth and orbits in the habitable zone of its star, the region where temperatures are right for liquid water to exist on the surface. The star is a red dwarf, smaller and cooler than our Sun, so the habitable zone is closer in, but the principle is the same. Not too hot, not too cold, just right for water to be liquid. We don't know if Kepler 186f actually has water. We don't know if it has an atmosphere or what that atmosphere might be made of. We can't even be certain it's a rocky planet rather than a gas world. But its discovery proved that Earth-sized planets exist in habitable zones around other stars, that worlds roughly like ours are out there, that the conditions necessary for life, as we know, it might be common rather than rare. Kepler 186f is 500 light-years away. With current technology, sending a probe would take millions of years. We'll probably never visit it, never know for certain what it's like, but knowing it exists expands our understanding of what's possible, of how many worlds might be out there, waiting to be discovered. Some exoplanets orbit 2 stars instead of 1, circumbinary planets, like the fictional Tatooine from Star Wars. If you stood on the surface of one of these worlds, you would see 2 suns in the sky, sometimes close together, sometimes far apart depending on their orbital positions. You would cast 2 shadows, their angles changing as the suns moved across the sky. The physics of these systems is complex. The planet must orbit both stars at a sufficient distance that the star's gravitational influences combine into something stable. Too close, and the competing gravitational pulls would destabilize the orbit, probably ejecting the planet entirely. But at the right distance, the system can be stable, with the planet following an elliptical orbit around the binary star system. These double sunsets and sunrises would create strange seasonal patterns, complicated lighting conditions, and presumably distinctive effects on any life that might evolve there. The rhythms of day and night would be different, more complex, varying in ways that single-star planets never experience. The Andromeda Galaxy is our nearest large galactic neighbor, sitting about 2.5 million light-years away. It's a spiral galaxy like the Milky Way, somewhat larger, containing roughly 1 trillion stars compared to our galaxy's few hundred billion. On clear, dark nights, Andromeda is visible to the naked eye as a faint smudge in the constellation Andromeda, the most distant object visible without a telescope. Andromeda is moving toward us at about 250,000 miles per hour. This seems fast, and it is by human standards. But at cosmic distances, this speed is almost stately. The galaxy is approaching because we're gravitationally attracted to each other, two massive objects drawing gradually closer, pulled together by the invisible force that shapes the universe. In about 4 billion years, Andromeda and the Milky Way will collide. This sounds catastrophic, and the event will certainly be dramatic, but collision is perhaps misleading. Galaxies are mostly empty space. The distances between stars are enormous compared to the stars' sizes. When the galaxies merge, it's highly unlikely that any two stars will actually hit each other. Instead, the galaxies will pass through each other like two clouds of gnats interpenetrating, with individual stars passing by other stars, but rarely colliding. But the galaxies won't pass through cleanly. Gravity will distort both galaxies, pulling out long streamers of stars, disrupting the spiral structure, eventually causing the galaxies to fall back together and merge into a single, large elliptical galaxy that astronomers have nicknamed Milkdromeda. The Sun and Solar System will likely survive this merger, thrown into a different orbit but intact, experiencing a brief period of spectacular sky displays as the galaxies interpenetrate, with unfamiliar stars appearing in unfamiliar positions, with the galactic core temporarily splitting into two bright centers before merging into one. The Black Eye Galaxy earned its name from its appearance, a dark band of absorbing dust in front of its bright nucleus, creating a structure that looks like a black eye, as if the galaxy has been bruised. This dark material is dust that absorbs visible light, blocking the light from stars behind it, creating a dark lane that contrasts dramatically with the bright galactic center. The Black Eye Galaxy is unusual in another way. The inner regions of the galaxy rotate in the opposite direction from the outer regions. This suggests that the galaxy absorbed a smaller galaxy in its past, with the merger creating this counter-rotating structure. The galaxy is a collision survivor, bearing the scars of its violent history in its structure and in that dark, dust-filled eye. The Sombrero Galaxy lives up to its name, looking like a wide-brimmed Mexican hat seen edge-on. It features a giant, flat ring of dust and gas surrounding a bright, bulging galactic core. The combination creates a distinctive profile, a glowing central sphere with a dark band across it, where the dust ring is seen in silhouette. The Sombrero Galaxy is notable for having an unusually large central bulge compared to its disk, suggesting it might actually be a hybrid, an elliptical galaxy that somehow acquired a disk, or a spiral galaxy with an unusually massive core. It also contains a supermassive black hole at its center, with a mass of about 1 billion suns, making it one of the most massive black holes in the relatively nearby universe. Zombie stars are white dwarfs in binary systems that have managed to trigger supernova explosions despite being dead. Here's how it works. A white dwarf is the remnant of a dead star, no longer fusing elements, just slowly cooling. But if this white dwarf has a companion star, and if that companion is close enough, the white dwarf's gravity can pull material off the companion. This stolen material accumulates on the white dwarf's surface, gradually adding mass. When the white dwarf reaches about 1.4 solar masses, the Chandrasekhar limit, something dramatic happens. The pressure at the core becomes strong enough to reignite nuclear fusion, but in an uncontrolled way. The entire star explodes in a Type Ia supernova, completely destroying the white dwarf. These supernovas are important to astronomy because they're very consistent in brightness. White dwarfs always explode at roughly the same mass, so the resulting supernovas are all roughly the same brightness. This makes them useful as standard candles for measuring cosmic distances. We can compare how bright they appear to how bright they actually are, and the difference tells us how far away they are. This is how we discovered that the universe's expansion is accelerating, a discovery that revealed dark energy. Dark energy is one of the deepest mysteries in physics. In the 1990s, astronomers studying distant supernovas expected to find that the universe's expansion was slowing down, decelerated by gravity pulling everything back together. Instead, they discovered the opposite. The expansion is speeding up. Galaxies are accelerating away from each other, driven by some force that works opposite to gravity. This force is called dark energy, though the name is misleading. Dark just means we can't see it, and energy is our best guess at what it might be. Dark energy appears to be a property of space itself, causing space to expand faster and faster. The more space there is, the more dark energy there is, creating a runaway effect where expansion accelerates continuously. Dark energy makes up about 68% of the universe's total energy content. Dark matter makes up another 27%. Normal matter, the atoms that make up stars, planets, and everything we can see, accounts for only about 5%. We're surrounded by, immersed in, composed mostly of stuff we don't understand, in a universe whose fundamental composition remains mysterious despite centuries of scientific progress. The Bhuta's Void is a massive region of space, roughly 330 million light-years in diameter, that contains almost no galaxies. Most regions of space this large would contain thousands of galaxies, but the Bhuta's Void contains only about 60, and most of those are clustered around its edges. The interior is almost empty, a vast dark bubble in the cosmic web. The void's existence surprised astronomers when it was discovered in 1981. We expect the universe to be relatively uniform on large scales. The cosmological principle suggests that the universe should look roughly the same everywhere. Large voids challenge this expectation, suggesting that structure in the universe is clumpier than simple models predicted. If our Milky Way had formed in the center of the Bootes void, our view of the universe would have been radically different. Other galaxies would be so distant, so faint, that we wouldn't have discovered they existed until the 1960s, when we developed powerful enough telescopes. Our entire understanding of cosmology would have developed differently, delayed by decades or centuries, fundamentally shaped by our position in an unusually empty region of space. Quasars are the brightest objects in the universe, powered by supermassive black holes actively consuming material. When material falls toward a black hole, it forms an accretion disk, a swirling disk of gas and dust that heats up from friction and gravitational compression, reaching temperatures of millions of degrees, emitting tremendous amounts of radiation across the electromagnetic spectrum. Quasars can shine with the light of 1,000 galaxies, outshining by 100 times the combined light of all 100 billion stars in a galaxy like the Milky Way. All this light comes from a region smaller than our solar system, making quasars the most luminous, persistent objects in the universe. The light from the most distant quasars has been traveling for over 12 billion years. We see these objects as they were when the universe was young, less than 2 billion years after the Big Bang. Studying quasars tells us about the early universe, about when the first supermassive black holes formed, about the conditions and chemistry of the cosmos when it was a fraction of its current age. In the constellation Aquila, there's a cloud of alcohol, ethyl alcohol, the same type of alcohol in alcoholic beverages that's billions of times larger than our solar system. This cloud contains enough alcohol to supply every person on Earth with a billion drinks. This isn't unique. Organic molecules including alcohols, sugars, and amino acids have been found in various places in space, in nebulas, and around young stars. These molecules form through chemical reactions in space, suggesting that the building blocks of life aren't rare, special creations of Earth, but common products of cosmic chemistry, potentially abundant throughout the galaxy. The existence of these organic molecules in space supports the idea that life's ingredients might be widespread, that the chemistry necessary for biology isn't unique to our planet, but is a natural outcome of the physical and chemical processes that occur wherever conditions are right. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general relativity and first directly detected in 2015. They're created by massive accelerating objects, typically by cataclysmic events like two black holes spiraling together and merging, or neutron stars colliding. These waves travel at the speed of light, carrying energy away from the events that create them, stretching and compressing space itself as they pass. When a gravitational wave passes through Earth, it stretches space in one direction while compressing it in the perpendicular direction, then reverses, creating an oscillation. The effect is incredibly tiny. The detectors that found gravitational waves can detect changes in length smaller than a proton, but it's real and measurable. Detecting gravitational waves opened a new way of observing the universe. Before, we could only see things that emit electromagnetic radiation, light, radio waves, X-rays. Now we can hear events through their gravitational effects, detecting collisions and mergers that might be invisible electromagnetically. We can study black holes not by seeing them, but by feeling the space-time vibrations they create when they collide. Space-time is often compared to a stretched fabric or rubber sheet, a two-dimensional surface that can be bent and warped. Massive objects like stars and planets create dents in this fabric, curves in space-time that we perceive as gravity. Objects moving through space-time follow these curves, which we interpret as gravitational attraction. This isn't just a metaphor or a visualization aid. Space-time is actually curved by mass and energy. The curvature is what gravity is. Newton thought gravity was a force acting at a distance, but Einstein revealed that gravity is the geometry of space-time itself, the paths objects follow through curved, four-dimensional space-time. This understanding predicts many phenomena that have been confirmed: gravitational time dilation, gravitational lensing, where light bends around massive objects, the precession of Mercury's orbit, the existence of black holes. General relativity is one of physics' most successful theories, confirmed by countless experiments and observations, yet still strange and counterintuitive, still challenging our intuition about space, time, and gravity. The cosmic microwave background, CMB, is the afterglow of the Big Bang, a faint radiation that fills every inch of the sky. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This recombination made the universe transparent for the first time. Before this, photons couldn't travel far without being scattered by free electrons. The CMB is the light from this moment, stretched by the expansion of the universe from visible and infrared wavelengths into microwave wavelengths, cooled from thousands of degrees to just 2.7 degrees above absolute zero. This radiation is almost perfectly uniform, the same temperature in every direction, but with tiny variations, fluctuations of about 1 part in 100,000. These tiny fluctuations are incredibly important. They're the seeds of all structure in the universe. The slightly denser regions that eventually collapsed to form galaxies and galaxy clusters. The slightly less dense regions that became the cosmic voids. The CMB is a baby picture of the universe, showing us what the cosmos looked like before stars existed, before galaxies formed, before anything we can see with telescopes had come into being. Let these alien horizons rest in your thoughts. Rogue planets drifting in eternal darkness, possibly outnumbering stars. HD 189733b, where glass rains sideways at 4,500 million Simtsig. The diamond world of 55 Cancri E Wasp 12b, darker than coal, slowly being devoured. J14 7b's rings, larger than the distance to the Sun. Kepler 180 CF in the habitable zone. Planets orbiting 2 suns. Andromeda approaching at 250,000 Mivoltnes. The coming merger into Milkdromeda. The Black Eye Galaxy with its dark bruise. The Sombrero's wide-brimmed profile. Zombie stars stealing life to explode. Dark energy pushing the universe apart faster and faster. The Baltic's void. 330 million light-years of almost nothing. Quasars, shining brighter than 1,000 galaxies. The giant alcohol cloud. Gravitational waves rippling through space-time. Space-time as curved fabric. And the cosmic microwave background. The universe's baby picture, still glowing faintly in every direction. This is the realm beyond our galaxy, where alien worlds orbit distant suns, where galaxies collide and merge, where the universe reveals itself as stranger than we imagined, filled with more wonders and mysteries than we can count. Rest here among the rogue worlds and alien horizons, in the space between galaxies where darkness is absolute, but phenomena shine brighter than we ever thought possible. And when you're ready, we'll complete our cosmic journey, exploring the very nature of the universe itself, its beginning and its eventual end, the deepest questions about existence and reality that science can address. We arrive now at the final frontier, at the edge of understanding itself, where science becomes philosophy and facts shade into speculation. This is the realm of ultimate questions. How does everything end? Are there other universes? Why does the cosmos seem so empty of life? What is our place in this vast, ancient, expanding reality? Let us drift together toward these deepest mysteries, toward theories of multiple universes and cosmic endings, toward the paradox of silence in a galaxy of billions of stars, toward the possibility of shortcuts through space-time and the photograph that shows Earth as a pale blue dot. Let us discover that the universe might be infinite, that time itself might be an illusion, that we are the cosmos awakening to contemplate its own existence. This is not a journey toward answers, but toward better questions, toward the humbling recognition that for all we've learned, the deepest mysteries remain. And there is peace in this, in accepting that some things cannot be known, that wonder is not diminished by understanding, but enhanced by it, that the universe is more strange and beautiful than we can imagine. The multiverse theory suggests that our universe, everything we can see, everything that exists within our cosmic horizon, might be just one bubble in a vast, infinite ocean of other universes. Each universe would be separate, perhaps with its own laws of physics, its own values for fundamental constants, its own history from its own Big Bang. In some versions of this theory, these other universes are unreachably far away, separated from us by more than distance, by barriers that cannot be crossed because they exist outside our space-time entirely. In other versions, they're constantly being created, new universes budding off from quantum fluctuations, baby universes being born in the foam of quantum mechanics. One particular interpretation of quantum mechanics, the many worlds interpretation, suggests something even stranger. That every time a quantum event occurs with multiple possible outcomes, the universe splits, creating parallel realities where each outcome happens. Every choice you make, every random quantum event, creates branching universes where different possibilities are realized. This means there might be universes where you made different choices, where history unfolded differently, where physics operates by slightly different rules. An infinity of variations, all existing simultaneously in a vast multiverse, all equally real, all inaccessible to each other. We can never know if these other universes exist. By definition, we can't observe them, but the mathematics of certain theories suggest they might be real. Our universe is expanding, and that expansion is accelerating. Galaxies are moving away from each other faster and faster, driven by dark energy. If this continues indefinitely, we face what cosmologists call the Big Freeze, the heat death of the universe. In this scenario, the expansion continues forever. Galaxies move farther and farther apart until each galaxy becomes isolated, unable to see its neighbors, alone in an expanding void. Within these isolated galaxies, stars continue their life cycles, born from gas clouds, burning their fuel, dying. But gradually, the gas gets used up. fewer new stars form. The existing stars age and die. Eventually, trillions of years from now, the last stars will burn out. The universe will contain only stellar remnants, white dwarfs cooling toward absolute zero, neutron stars and black holes, brown dwarfs that never quite became stars, planets orbiting dead suns in eternal darkness. The night sky, already increasingly empty as expansion pushes galaxies beyond the visible horizon, will become completely black. In this distant future, the universe reaches a state of maximum entropy, of perfect disorder, of equilibrium at just slightly above absolute zero. No gradients exist to drive any process. No energy remains to do work. The universe becomes perfectly, absolutely quiet. Not silent like space is silent now, but dead, devoid of any change, any event, any process. Time becomes meaningless because nothing happens, nothing can happen, nothing will ever happen again. But this is just one possibility. Another theory suggests a different fate, the Big Crunch. In this scenario, gravity eventually wins the cosmic tug-of-war against expansion. The universe stops expanding, reverses course, and begins to contract. Galaxies start moving toward each other. As the contraction accelerates, galaxies collide and merge. The space between everything shrinks. Eventually, everything collapses back together into a single point, a cosmic singularity where all matter and energy are compressed to infinite density, where the laws of physics break down, where time and space cease to have meaning. The universe ends not in cold and darkness, but in heat and compression, in a reversal of the Big Bang. Some versions of this theory suggest a big bounce, the idea that the crunch leads to a new explosion, a new Big Bang that creates a new universe. Perhaps this has happened before, perhaps infinitely many times, creating a cyclic cosmos where universes are born, expand, contract, and are reborn in an eternal rhythm. Our Big Bang might have been preceded by an earlier universe's Big Crunch, and our eventual crunch might seed the next universe's bang. The Big Rip is the most violent of the proposed cosmic endings. In this scenario, dark energy, which is currently accelerating the expansion, doesn't remain constant but grows stronger over time. As space expands faster and faster, eventually the expansion overwhelms not just the gravitational bonds holding galaxy clusters together, but the gravity holding galaxies together, then solar systems, then planets, then molecules, then atoms. In the final moments before the Big Rip, space expands so fast that it tears apart the fundamental structure of matter. Atoms are ripped apart, their electrons torn away from their nuclei. The nuclei themselves are torn apart, protons and neutrons separated. Even subatomic particles might be torn apart if space expands fast enough. The universe ends in a cascade of disintegration, everything that exists being shredded by the expansion of space itself. Fortunately, or perhaps unfortunately for those who enjoy dramatic scenarios, current observations suggest the Big Freeze is the most likely fate. Dark energy appears to be constant rather than increasing, and the universe's density is below the critical value needed for a Big Crunch. But these endings are so far in the future, trillions upon trillions of years, that the numbers are almost meaningless to human comprehension. The universe is young, and its ending, by whatever mechanism, is incomprehensibly distant. The Fermi paradox is named after physicist Enrico Fermi, who reportedly asked during a lunch discussion, "Where is everybody?" paradox is this. The Milky Way contains hundreds of billions of stars, many with planets, many of those planets potentially habitable. The galaxy is billions of years old, giving plenty of time for life to arise and evolve. If even a small fraction of suitable planets develop intelligent life, and if even a small fraction of those civilizations develop technology for space travel or communication, we should see evidence of alien civilizations. They should be everywhere, but we don't see them. We don't detect radio signals clearly of artificial origin. We don't see evidence of large-scale engineering projects like Dyson spheres around distant stars. We don't observe spacecraft or probes visiting our solar system. The galaxy appears empty of other intelligence. This absence is the Fermi paradox, the contradiction between the expectation of abundant alien life and the observed absence of any evidence for it. Many explanations have been proposed. Perhaps intelligent life is extremely rare. Perhaps the conditions for life are more restrictive than we think. Perhaps civilizations inevitably destroy themselves before they become spacefaring. Perhaps interstellar travel is simply too difficult and civilizations stay home. Perhaps aliens exist but don't communicate in ways we can detect. Or perhaps they're avoiding us deliberately. Or perhaps we're first. Perhaps we're among the earliest intelligent species to arise, and the others haven't evolved yet. Or perhaps we're alone. Perhaps life, despite the abundance of planets, is so improbable that it's happened only once in the observable universe. This would make Earth precious beyond measure, the only place in the cosmos where matter has organized itself to contemplate its own existence. The great silence, the absence of any detected alien signals, continues. We listen, we search, we analyze every unusual signal, but so far, only silence answers. We are, as far as we know, lonely islands in a cosmic ocean, searching for other islands that may not exist, or that may be so distant that the ocean between us is impossible to cross. Somewhere in space, hidden behind the plane of the Milky Way, where dust obscures our view, lies the Great Attractor, a mysterious gravitational anomaly pulling our galaxy and thousands of others toward it at hundreds of kilometers per second. We can't see it directly, but we can measure its effect on the motion of galaxies, the way their velocities indicate they're being pulled towards something massive. The Great Attractor appears to be a concentration of mass, perhaps a large galaxy cluster, perhaps a structure even larger, exerting gravitational influence over an enormous region of space. Our local group of galaxies, the Virgo cluster, and thousands of other galaxies are all being pulled in its direction, flowing through space like water flowing toward a drain. What makes the Great Attractor particularly mysterious is that we can't observe it well because it's behind the galactic plane, obscured by the dust and stars of our own galaxy. We're trying to understand something massive and important while our view is blocked, like trying to see a mountain while standing in a thick forest. We know it's there. We can feel its effects, but we can't see it clearly. Recent observations suggest the Great Attractor itself is being pulled toward an even larger structure called the Shapley supercluster, part of a vast network of galaxy clusters and filaments that make up the universe's large-scale structure. We're not just falling toward the Great Attractor, we're part of an even larger flow, a cosmic river of galaxies moving through space in response to the gravity of the largest structures in the universe. The pillars of creation, those iconic columns of gas and dust in the Eagle Nebula, may already be gone. Astronomers have observed evidence of a supernova explosion near the pillars that likely occurred about 6,000 years ago. The shock wave from this explosion would have struck the pillars, heating and dispersing them, probably destroying them. But we're seeing the pillars as they were about 7,000 years ago. That's how long it took their light to reach us. If the supernova happened 6,000 years ago, its light hasn't reached us yet. We won't see the pillar's destruction for another 1,000 years or so. We're looking at a structure that may already be gone, seeing the past, watching ghosts of gas clouds that may no longer exist. This illustrates a strange feature of astronomy. We never see the universe as it is now, but always as it was, looking back in time by amounts that depend on distance. The farther away something is, the older the light we're seeing. The universe is a time machine, showing us history, never the present. General relativity allows for some strange solutions to its equations, including wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe, creating shortcuts that would allow travel between them without crossing the intervening space. If wormholes exist and can be stabilized, which would require exotic matter with negative energy density, which we've never found, they could theoretically allow faster than light travel in a sense, not by moving faster than light through space, but by taking a shortcut through space-time itself, emerging at a distant location without having traversed the space between. However, wormholes remain purely theoretical. We don't know if they can exist in reality, and even if they can, we don't know if they could be created, stabilized, or traversed. They're mathematical possibilities that emerge from Einstein's equations. But mathematics allows many things that nature may forbid. Wormholes represent hope for interstellar travel, a potential way around the light speed limit that makes the universe so difficult to explore. But they remain firmly in the realm of speculation. White holes are the theoretical, mathematical opposites of black holes. While nothing can escape from inside a black hole's event horizon, nothing can enter a white hole. It would expel anything that approached, radiating matter and energy outward. If black holes are points where space-time curves infinitely inward, white holes would be points where space-time curves infinitely outward. There's no evidence that white holes exist in reality. While they're solutions to Einstein's equations, they appear to be unstable and would violate the second law of thermodynamics in most scenarios. They remain mathematical curiosities, interesting for what they reveal about the structure of general relativity, but probably not real features of the universe. The concept of a habitable zone, often called the Goldilocks zone because conditions are just right, is the region around a star where temperatures allow liquid water to exist on a planet's surface. Not too close to the star, where water would boil away, and not too far where it would freeze. Earth sits comfortably in our sun's habitable zone, and we're finding thousands of planets around other stars that also orbit within their star's habitable zones. This doesn't guarantee these planets have life, or even liquid water. Atmosphere, planetary composition, magnetic fields, and many other factors matter too. But it's a starting point, a way to narrow the search for worlds that might be habitable, that might harbor life. that might be worth investigating more closely. On August 15, 1977, a radio telescope at Ohio State University detected a strong narrowband radio signal that lasted 72 seconds. The signal was so remarkable that the astronomer reviewing the data wrote "Wow" in the margin, and the signal has been known as the WOW signal ever since. The signal had characteristics that made it seem artificial: a narrow frequency band, strong intensity, and a pattern consistent with coming from deep space. It appeared to originate from the direction of the constellation Sagittarius, and it bore many hallmarks of what we might expect an extraterrestrial signal to look like. But the signal was never detected again. The telescope searched the same region of sky repeatedly. Other telescopes looked for it, but nothing. The WOW signal remains unexplained. Was it aliens? Probably not. Most scientists think it was likely some kind of interference or natural phenomenon we don't fully understand. But we don't know for certain. And the signal remains one of SETI's most intriguing mysteries, a tantalizing hint that might mean nothing or might be the closest we've come to detecting an extraterrestrial civilization. Astronomers have discovered a reservoir of water vapor surrounding a quasar about 12 billion light-years away. This water vapor contains 140 trillion times as much water as all of Earth's oceans combined. The water exists as vapor in the quasar's environment, heated by the radiation from the supermassive black hole at the quasar's center. This discovery demonstrates that water, essential for life as we know it, has been common in the universe since nearly the beginning, existing when the cosmos was only about 1/10 of its current age. Water isn't a recent development or a rare molecule, but a fundamental part of cosmic chemistry, formed easily and existing abundantly, suggesting that one of life's essential ingredients is widespread throughout space and time. Planets and stars emit various types of electromagnetic radiation, including radio waves. NASA and other space agencies have recorded these radio emissions and converted them into sound files that humans can hear, a process called sonification. The result is eerie, haunting, sometimes beautiful space sounds. The radio voice of Jupiter, the electromagnetic song of Saturn, the solar wind made audible. These aren't sounds in the traditional sense. Sound waves can't travel through space's vacuum, but they're translations of real phenomena into a form we can perceive, making visible, or in this case, audible, the otherwise invisible electromagnetic environment of space. The sounds are strange and otherworldly, whistles and clicks and hums, reminding us that space isn't the empty silence we imagine, but is full of activity and phenomena, just not the kind our unaided senses can detect. The ancients spoke of the music of the spheres, a philosophical concept that the movements of celestial bodies created a form of music, inaudible to humans but mathematically perfect, a cosmic harmony. Modern space sonification is, in a way, the fulfillment of this ancient idea. We can now actually hear the planets sing, converted from electromagnetic to acoustic waves, making audible the music that was always there. On February 14, 1990, at Carl Sagan's request, Voyager 1 turned its camera back toward Earth from a distance of 3.7 billion miles and took a photograph. In that image, Earth appears as a pale blue dot, barely visible, occupying less than a single pixel, a tiny speck of light against the vastness of space. Sagan wrote beautifully about this image. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. The pale blue dot image provides perspective like nothing else. All of human history, every triumph and tragedy, every empire and civilization, every war and peace, every love and loss, all of it happened on that tiny, fragile speck. The image is humbling and exalting simultaneously. Humbling because it shows how small we are. Exalting because that tiny dot contains everything we've ever known, every person we've ever loved, all of human achievement and potential. The image reminds us that Earth is precious, that in all the vastness of space, this is the only home we've got, the only place we know of where life exists, where matter has organized itself to create consciousness and art and science and love. We should cherish it, protect it, recognize how rare and valuable it might be in a cosmos that seems so far to be mostly empty of life. When cosmologists map the universe's large-scale structure, the distribution of galaxies and galaxy clusters, a striking pattern emerges. Galaxies cluster along filaments, long structures of matter with vast voids between them, creating a web-like appearance often called the cosmic web. Remarkably, this structure bears a striking resemblance to neural networks in the human brain. The brain's neurons are connected by axons and dendrites, creating networks of connections with neurons clustered along these pathways. The similarity between the cosmic web and neural networks is superficial. They're made of completely different things and operate by completely different principles. But the visual resemblance is striking. This similarity has led to speculation about whether the universe itself might be a kind of conscious entity, whether the patterns reflect some deep organizing principle that operates at all scales. These ideas remain firmly in the realm of philosophy rather than science. There's no evidence the universe is conscious in any meaningful sense. But the pattern reminds us that similar structures can emerge from different processes, that the universe favors certain organizational patterns across wildly different scales and contexts. Entropy is a measure of disorder, and the second law of thermodynamics states that entropy in a closed system always increases over time. This law gives time its direction, its arrow. We remember the past, but not the future, because the past was lower entropy, more ordered, and the universe naturally evolves toward higher entropy, more disorder. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. Processes run in one direction because that's the direction of increasing entropy. Entropy explains why the universe changes, why time seems to flow forward, why we age, and why stars eventually die. The universe is gradually running down, moving toward maximum entropy, toward heat death, toward the big freeze we discussed earlier. Entropy is cosmic time's heartbeat, the rhythm that ensures change happens, that distinguishes past from future, that makes the universe dynamic rather than static. Some theories suggest the universe might be infinite, not just in spatial extent, but in temporal extent, existing forever into both the past and the future. In these models, the universe has no beginning and no end, no first moment and no last moment, just an eternal existence stretching infinitely in both temporal directions. If the universe is infinite in this way, the Big Bang wasn't the beginning of everything, but just a phase transition, a moment when our observable universe went from one state to another, perhaps emerging from a pre-existing state that itself had no beginning. Time would be truly eternal, with no edge, no starting point, no moment of creation, just infinite existence. These ideas are speculative and difficult to test. How do you prove something is infinite? But they address deep questions about causality and existence. If the universe had a beginning, what came before? What caused the beginning? An infinite universe avoids these questions by denying that there was a beginning, by asserting that existence is fundamental and eternal, that time and the universe simply are, without need for creation or origin. As you look up at the night sky, you're looking at the universe, but you're also part of it. You're not separate from the cosmos, but a piece of it, matter organized in a particular way, atoms borrowed temporarily from the universe to create the pattern that is you. When you gaze at stars, you're the universe looking at itself, matter contemplating matter, consciousness examining its own origins. This perspective, that we are the universe become self-aware, can be deeply meaningful. We're not observers from outside, but participants, expressions of the cosmos's fundamental nature. The atoms in your body were forged in stars, scattered by supernovas, gathered into planets, eventually organizing into life and consciousness. You are stardust that has learned to wonder about stars. And in the end, perhaps the most relaxing fact about deep space is this: we are forever connected to the silent, beautiful infinity. We came from it, we're made of it, and eventually we'll return to it, our atoms recycled, continuing the cosmic story. We're temporary patterns in an eternal dance, brief melodies in an endless symphony, small but genuine parts of something vast and magnificent and mysterious. The universe is old and large and mostly empty, but it's also beautiful and governed by comprehensible laws, and it's capable of producing worlds and life and consciousness. For all its vastness, for all its violence and strange physics and incomprehensible scales, it created us, and that alone makes it worthy of wonder. Let these final facts rest gently in your awareness. The multiverse theory suggesting infinite other universes. The big freeze, where the last stars burn out into perfect quiet. The big crunch pulling everything back together. The big rip tearing apart even atoms. The Fermi paradox asking, where is everybody? The great attractor pulling thousands of galaxies. The pillars of creation possibly already destroyed, but still visible. Wormholes as theoretical shortcuts. White holes expelling everything. Thousands of planets in Goldilocks zones. The wow. Signal never repeated. Water reservoirs holding 140 trillion times Earth's oceans. NASA's space sounds making planets' music audible. The pale blue dot showing Earth as a fragile speck. The cosmic web resembling neural networks. Entropy as time's arrow. The possibility of infinite time. You as the universe observing itself. And the eternal connection between us and the silent, beautiful infinity. This is the great mystery, the final frontier, not of space, but of understanding. These are the questions that science approaches, but cannot fully answer. The boundaries where physics meets philosophy, where measurement meets meaning. The universe is comprehensible yet mysterious, vast yet intimate, ancient yet ever renewing, full of endings but also full of beginnings. Rest now in this cosmic perspective, in the knowledge that you are made of stars, that you're part of something immense and ancient and beautiful, that your brief existence is connected to everything that is, that the atoms in your body have existed since nearly the beginning of time and will continue existing long after your pattern dissolves. You are temporary but real, small but significant, mortal but connected to the eternal. The universe is vast and we are tiny, but we are conscious pieces of the universe trying to understand itself, and that makes us precious beyond measure. Sleep well, cosmic Voyager. Dream of stars and galaxies, of black holes and nebulas, of the infinite patience of space and the ancient light of distant suns. You are at home in the universe because you are the universe, and the universe is, in every way that matters, your home. Good night. Rest in the peaceful infinity, in the gentle darkness between stars, in the knowledge that you are stardust, contemplating stardust, a way for the cosmos to know itself. The universe is vast and mysterious and beautiful, and you, unlikely, improbable, temporary you, are part of it, forever connected to the great cosmic dance. Sleep well among the stars. You belong here, in this corner of space, on this pale blue dot, part of the universe's story. And that story, despite all its mysteries and uncertainties, despite its incomprehensible scales and eventual endings, is beautiful beyond words, worthy of wonder, and infinitely worth experiencing. Good night.